Okay, let's take a look at number 32. This is the first part 3 question in the August 2022 Geometry Regents exam. As modeled in the diagram below, a building has a height of 50 meters. The angle of depression from the top of the building to the top of the tree is 13.3 degrees. The angle of depression from the top of the building to the bottom of the tree is 22.2 degrees. And we want to find to the nearest meter the height of the tree. So our ultimate goal is figuring out the length of TB. Now, the problem here is that we are given a right triangle. We actually have two right triangles. So what I'm going to do is I'm going to mirror that right angle from down here up at the top. And I'm actually going to copy over the 50 meters as well. Okay. Basically looking at this picture in terms of a big rectangle. What I'm also going to do is I'm going to just draw the pictures separately. So I have the top triangle, so I'll color code them here so you can see a little bit better. But here's the top triangle. I know the angle is 13.3 and I have the right angle. And then I have, so that's this triangle. Then I have the one that I'll highlight in green. And that's the bigger right triangle. For that triangle, the angle is 22.2, and I do know that this is 50. Okay, based upon what I have so far, I can see that if I go and try and set up an equation in this first triangle, the one I highlighted in blue, I'm missing too much information. So I'm actually going to start over with the green one. And I'm going to say, let's try and find this side first. And I'll show you why that's helpful. Because when we're looking for this, here's going to be our ultimate goal. We know that this whole distance is 50 over on the right. If we could figure out this value, let's call that y. And I'll copy that over to the blue triangle as well. If I can find that value of y, I can subtract 50 minus y, and that will give me the length of TB, basically the length or the height of the tree. So let's start with our green triangle here. So I am going to use tangent. Very often these double trig problems, as I call them, are using tangent. I'm going to cross multiply. So tangent is opposite over adjacent. And I'm going to divide to get x by itself. Okay, typing that into my calculator. I have x is 122.521,259,8944. I am not going to round this value. The reason is it's not my final answer. It asks us to round to the nearest meter the height of the tree. This does not represent the height of the tree, so I'm just going to leave all of those decimals in there. So I could copy that value up onto the big picture. Or if you prefer just working with the new picture, you could copy that value over here too. So here's the reason I said I would explain why we are going to find that missing side of x first. The reason is because that side is part of the blue triangle and it's part of the green triangle. It's a shared side of both of them. So now that allows me to take this value and have an actual piece that I could plug in to a SOHCAHTOA or a trig equation for this triangle. So now I can use tangent again, opposite over the adjacent, which is our new side. I could put that over 1 and cross multiply. And I get that y is 28.9627985431. So the length of the segment TB, or the height of the tree, is going to be 50 minus that value. And in this problem, we're going to make sure we follow our rounding directions. It asks to the nearest meter, so that is going to be 21 meters. For number 33, we are given that the coordinates of the vertices of quadrilateral HYPE are blah, blah, blah. We want to prove that this is a rectangle. Anytime it says the use of the set of the axes below is optional, I would use them. I think graphing it just makes it a little easier to see. So I have already gone ahead, plotted my 4 points, and I can see it does look like a rectangle, but we need to actually prove it is. And we're going to use coordinate geometry formulas to do that. There are different ways to do it. You have to think about some properties you know about, in this case, a rectangle. So one thing I know is in a rectangle, the opposite sides should be congruent. So HY and EP should be congruent. YP and HE should be congruent. But I also know that the diagonals are congruent. In order to show congruency or length in a coordinate proof, we are going to use the distance formula. So I'm going to set up the 6 distance formula calculations that I need to find. So I'm going to first do the 4 sides. And then I'm going to, I'll just split this here just so you see, find the lengths of the 2 diagonals as well for a total of 6 calculations. All right, for my distance formula, I'm going to subtract the x's, square it, subtract the y's, square it. Doesn't really matter which order you subtract the x's and the y's in because you're squaring it anyway, so we'll come out to the same answer. So this is going to give me 25 plus 9 inside the radical, that's 34. So HY is radical 34. Okay. Now let's continue on. YP, subtract the x's. Subtract the y's, and I get 136. To get that answer, by the way, I would just do this. I would find the value of what's inside the radical without actually putting the square root into your calculator. Okay. All right, next, PE. 5 squared plus 3 squared. Again, if you have a -5 in there or a -3, that's fine. We'll get the same answer in the end. Radical 34, that seems familiar, so that's important. And then 6 squared and 10 squared and radical 136 again. Great, we've shown that opposite sides are congruent, right? HY and PE, for instance, we said are opposite sides. Now let's show the diagonals are congruent. So HP, subtract the x's, I get 11. Subtract the y's, and I get 7. So in this problem, I have 121 basically, right? 11 squared plus 49, and we get the square root of 170. You could also have used Pythagorean theorem to find any of these side lengths, by the way. YE, subtract the x's, and I am going to get 1 squared plus 13 squared, and that will give us 170, radical 170 as well. Keep in mind, these problems are not saying, is it a rectangle? It's saying, prove it is. We need to make sure our numbers work out. So if you don't get these matches in here, like the radical 34s that match, for instance, definitely go back, check your work. All right, to finish this off, we're going to write a sentence or two concluding how we know that this is a rectangle. So I'm going to say HYPE is a rectangle because, and now let's just explain what we showed with our work. We showed opposite sides are congruent and the diagonals are congruent. And that finishes off number 33. Okay, for number 34, a packing box for baseballs is the shape of a rectangular prism with dimensions of 2 feet by 1 feet or 1 foot by 18 inches. Each baseball has a diameter of 2.94 inches. Well, let's notice immediately the mismatch of units and get them to be uniform. So I'm going to say this is 24 inches, 12 inches, and now everything has the same unit of inches. I'm also going to just take note that this number is really close to 3. It's going to be harder to figure this problem out when you use 2.94, but 3 is a nice clean number. And if you notice, all of these numbers over here are divisible by 3. So that's going to make things a little bit easier. All right, determine and state the maximum number of baseballs that can be packed in the box if they're stacked in layers, and each layer contains an equal number of baseballs. So the box is in the shape of a rectangular prism. If you want, you could draw this out to try and visualize it. We know that this is 24 inches across, this is 12 inches, and then our height is 18 inches. We know that each baseball has a diameter. Okay, so if I'm looking at a baseball here of 3 inches. So I have to think about, well, how many can I fit across here? So if the length here is 24 and each one is 3, 24 divided by 3, I can fit 8, 1, 2, 3, 4, 5, 6, 7, 8 baseballs across that way. Going back, I can fit 4. And then I can, going up, fit 6. And this is not exactly what it's going to look like in the box. This is, of course, just our little estimate. So we can really do 8 by 4 by 6, which gives us a total of 192 baseballs. Now it says the weight of a baseball is approximately 0.025 pounds per cubic inch. This is a unit for density. Density is mass over volume, and this is a unit of mass, pounds, per a unit of volume, cubic inches. Determine and state to the nearest pound the total weight of all the baseballs in the fully packed box. All right, well, let's find the volume of a baseball. The formula is on your reference sheet. Volume is 4/3 pi r cubed. The radius was not given to us, but the diameter was. So the diameter is 2.94. Let's have that. So my radius is 1.47. Let's cube it. And we know that there's 192 baseballs in the box. So I'm going to multiply that by 192. All right, let's type that in here. 4/3 pi 1.47 cubed. Just be careful. This is the only formula with a cubed. The other volume formulas are squareds. So an easy mistake to mistype that. And we're going to multiply that by 192. So the volume of all of the baseballs in the box is 2,554. And all of these decimals, which I'm going to keep right now because this is not my final answer. So I'm not going to round yet. And now let's work with that density. Density is mass over volume. So 0.025 is equal to the mass over that volume we just found. If I put that over 1 and cross multiply, here's what we get. And we're asked to round to the nearest pound, so the nearest whole number, and I get 64 pounds. Okay, our last problem in this Regents exam is a part 4. So this is a 6-point question, and it is a proof. When you get a proof, there's really 3 options for types of proofs. There's coordinate proofs, like the rectangle one we saw earlier in this video. There's congruent triangle proofs, where the triangles are the same size, and there's similar triangle proofs. It helps if you know right off the bat which one you're working with. So I can tell right off the bat I'm working with similar triangles, because if you just glance at the triangles in your picture, they are not the same size, so I can't be possibly proving them congruent. So I know I'm looking for similar triangles. So I'm just going to put some notes off to the side. That's how I know I am looking for similar triangles. Pretty much every single similar triangle proof, you're going to prove the triangles are similar by angle-angle similarity theorem. Okay. So my goal is to prove that 2 angles in triangle AEH are congruent to their corresponding angle in triangle CFH, and then we'll deal with the proof statement. But first, let's just get the triangles to be similar to one another. All right, so I've gone ahead and set up my 2 columns, wrote my givens in, and now let's read through those givens together. So we have quadrilateral ABCD, AC and EF intersect at H. EF is parallel to AD. So I'm just going to put these little parallel arrows here to indicate that. And EF is also parallel to BC. I also know that AD and BC are congruent to one another. Okay. So based on this, I have to, again, work with those two triangles. So let's think about, once you write the givens, you want to think about how can you elaborate upon them? Is there anything in the givens that you can explain more about? So I noticed that if I have a quadrilateral where one pair of opposite sides are congruent and parallel, that is in fact a parallelogram. So I'm going to say for line 2 that ABCD is a parallelogram. And my reason behind that is going to be a quadrilateral. We're explaining how we know it's a parallelogram. So a quadrilateral where one pair of opposite sides are congruent and parallel is a parallelogram. Of course, we know that this is going to be true for both sides, and we're going to talk about that in a second. Now I know that AB must be parallel to CD because opposite sides of a parallelogram are parallel. So I'm going to put, just like, since they're second pair of sides, I'm going to put 2 arrows on those. Here's why that's important. If I have parallel lines, I know that I'm going to get congruent alternate interior angles, and those can be found in a Z shape. So the Z shapes that we look for can be forward-facing Z's, backwards, sideways, but here's the one I'm going to use here. So if you take a look, and I highlight the sides that we just said are parallel, and I highlight the side that connects them. So in this case, AC, segment AC connects them. You can see this backward Z shape. So the angles that are in the corners of the Z are going to be congruent alternate interior angles, and that's what we're going to write about in our next 2 lines. So I'm going to say that angle EAH and angle FCH are alternate interior angles. And the reason is parallel lines cut by a transversal form alternate interior angles. But we also want to say they're congruent. So in line 5, I'm going to say those 2 angles are congruent because alternate interior angles are congruent. So remember before we said that we want to get angle. We now have 1 angle per triangle. We have to find another, and the way we're going to do that is by utilizing vertical angles in here. Vertical angles, there's also a little hint up here for it that you have intersecting lines. That's how vertical angles are created. All right, so I'm going to, they give you 2 pages generally for number 6 here, for the 6-point question, excuse me. So I'm going to basically extend my table here, and I'm going to start talking about those angles being vertical angles. So angle AHE and angle CHF are vertical angles. And my reason behind that is intersecting lines form vertical angles. If you're feeling like this is a long proof, it is. 6-point questions are going to be lengthy for sure. All right, in the next line, let's say those angles are congruent. And that's because vertical angles are congruent. Now we have two angles marked off in each triangle. So I could say that triangle AHE is similar to triangle CHF by the angle-angle similarity theorem. All right, now I said once we get the triangles to be similar, we'll deal with what that proof statement has to be. So basically the proof statement is asking us to show that EH times CH is equal to FH times AH. If you think about similar triangles, the corresponding sides are proportional. These four sides are two pairs of corresponding sides, but they're being multiplied. They're not in a proportion. So what I'm going to actually do is I'm going to put them in a proportion. So for line 9, I'm going to say, and you could even set up your proportion first. I'm going to fill this in. I'll explain how I'm filling this in just a second. I'm going to create a proportion using those four segments. And here's how I knew how to put them. When you multiply or cross multiply, EH is going to be multiplied by CH. Look up here. That's what we need to do in our proof statement. And FH is going to be multiplied by AH. So I undid the cross multiplication and stuck it back in a proportion. So this is because corresponding sides in similar triangles are proportional. And that can often be abbreviated with CSSTP. Finally, our proof statement. Cross multiply this proportion right here. You have EH times CH equals FH times AH. And how do we know that those are equal? Well, that's what happens when you cross multiply, right? So let's write that a little nicer here. So we're going to say cross products of proportions are equal. And yes, it is definitely a lengthy proof, but again, any 6-point question is going to be time consuming, but that is our completed answer to number 35. Be sure to check out the rest of my channel to see other Geometry Regents review solutions.